who will be ahead in AI technology by 2030, India or Israel? Like you said, over the next 10 years. And you are like in the lion's den, and you get asked this question, right? And I stupidly said India. And all of my colleagues were looking at me, what's wrong with you, Raja? Right? We're here, and all the stuff. What's that? And when the whole thing ended, we were leaving. He came up to me, and he said, "You're absolutely right." Right. And at the end of my talk, I'll tell you what he said, why that was the case. Okay. So I am jet lagged. So I may say some stupid things again, right? So, I apologize in advance. But there is this, I want to start my real talk with this statement. This is a gentleman named Rich Sutton, a pioneer in AI. When I talk about AI, it is, this statement I go by, right? He says the biggest lesson that can be read from the 70 years of AI research. There's lots of buzzwords, lots of stuff, lots of cool things everybody talks about. But he says the general, simple methods of computation are ultimately the most effective, right? Some call it brute force, right? That's because Moore's law made this general purpose computation cheaper, affordable, and all. And one theme that you see over the last, 60 years, 70 years of technology progress is this notion of democratization of compute or democratization of technology. When we made a lot of compute available to a lot of people, major disruptions happened, right? Things that we didn't imagine, right? If you look at the PC era, which I grew up in, when we got 1 billion people access to a PC, right, the whole internet happened. We didn't, right now we look backwards and call that the Web 1.0 era, right? That was the end of the PC era, right? It was Web 1.0. And we digitized everything we could. Right now you have access to so much information, as Dr. Shiva was talking about, 118 zettabytes. We networked everything we could, Web 1.0. And if you see, on the y-axis, I have the compute accessible to people. I know the display is not very good here, but it keeps going up, from a few kiloflops to megaflops to, teraflops. And when we got to the mobile and cloud era between 2000, after 2000, right, we got everybody connected to mobile. Everything is connected to a cloud, right? And India did very well on the mobile side, right? And these numbers may be a little dated. We may be over 1 billion now, or 800 million smartphones, highest data consumption per user, lowest cost per bit. I'll come back a little later to show that India didn't do that well on cloud. Okay, we'll talk about that in a second. That's what happened. And now, so that's the past. What's the future, right? And this was the Web 2.0. Everyone talks about Web 3.0 now, right? I like to call it the distributed intelligence era, where there'll be over 1 trillion devices, trillion intelligent devices, by the time we get to 2030, right? Just imagine, right? From 1 billion PCs to 1 trillion intelligent devices, right? That is the market. That is what it's going. In fact, today, as we speak, there was a Google talk recently. They said there are 300 billion of this, right? No wonder we have supply chain crisis, right? All of them need silicon, okay? Now, the y-axis, see, it keeps going up. If you want the device to be intelligent, it needs lots of computing. The demand for AI computation, this whole deep learning, has been outpacing Moore's law, right? So every 3 to 4 months, the size of the network we can train and get something useful out has been doubling the compute demand on the y-axis. In fact, to train the most recent networks within the next 3-4 years, we need a zetta-scale, the 10 to the power of 21, as Dr. Shiva said, all the stars in the universe level compute to train these neural nets, right? That is, the framing for zetta-scale. Now, there are many, many reasons why you need more compute, okay? I decided not to go into the why aspect of compute today. That's a whole another presentation. But trust me, we will all need a lot of compute. Access to compute is as basic as access to air, water, and other natural things that we all live by. And this compute is necessary from sensors to edge to data center. Why, right? We're generating, Dr. Shiva said 118 zettabytes. We are on trajectory to 175 zettabytes over the next 5 years on instantaneous data that's being generated by users. You can't move all of this data from sensors to data center every millisecond. It's huge, humongous waste. You want to compute, you want to get the insights of the data where they're generated, throw the garbage away, and send the insight to where you want to store, right? And if you look at the computational capabilities today, we have sensors, right? I'd like to use like the neurons for the sensors, and I'll get to why that is. At the edge, we have teraflops, right? If you have an iPhone in your pocket, iPhone 13, it's a teraflop GPU inside that iPhone, okay? That's not a big number. It used to be a supercomputer 15 years ago, right? Size of this whole room that we are in here. Now, petaflops will be at the edge. I'll show it to you in a second. I think I have my petaflop thing sitting there. I'll show that in a second when I show the, yeah. So this is a petaflop GPU that I can hold in my palm, right? I'll show you what it's built on. And the data centers are going to exaflops, right? US is building 3 exascale supercomputers. So is China. So will Europe. Now, the demand for the AI compute, if you look at by 2025, we need at each of these places a 1,000x increase in compute. We need over a billion neuron capability. And now you look at billion neurons, sounds big, but human brain is of the order of 100 billion neurons, right? So it's not that big to mimic a brain, but to do your basic surveillance cameras or other edge equipment, you need that level of compute sitting at the edge. The left side of the edge needs petaflops, like I show, right? I used to joke, it was in 2016, I said, I'll have a petaflop computer in my Tesla, and everybody laughed at me, right? And they said, oh, why do you need a petaflop computer in a Tesla? And today, if you go to San Francisco, all of the Waymo cars that drive around collecting data and doing the autonomous driving have a petascale computer sitting inside them in 2022. Edge will go exaflops, and data centers will go zettaflops of AI compute. That's what we need to get to in 25. Now, it's not going to be easy to get to this, right? I mean, the demand exists, but the technology still has challenges. And that's the opportunity for India that I want to highlight, right? These numbers that I put on PowerPoint, the beautiful thing about PowerPoint is you can make up anything, right? It's just, multiply by 1,000, put 3 numbers, and say by 2025, we get zetta-scale. Unfortunately, we haven't still invented a technology that can take PowerPoint and get a product out, right? Now, if you look at those numbers, okay, and now speaking of manufacturing, why Intel and Pat talks a lot about manufacturing. We are talking about over 1 trillion connected devices, or 1,000x more compute, And even if you assume perfect Moore's law is going on, doubling every 2 months, every 18 years, you need about 100x more wafer capacity than exists in the world today, right? About 100x more wafer capacity, okay? Whether that is in form of 100x more fabs or fabs that produce smaller number of fabs that produce more, that's what is needed. This is why we need to build the capacity everywhere. Now, the rest of my talk will be about the full stack that we require. The semiconductor ecosystem, getting to zetta-scale, is not just about silicon. It is about silicon, systems, and software, right? And I use the word architecture. So, the most famous computer architecture book is from Patterson and Hennessy. In that book, in the first edition or something, they have this funny picture. This picture actually is stolen from that book, where they have this hardware guy, right, like a little grumpy-looking, unhappy person like Jim Keller yesterday, right? And then there is this ISA contract, right, instruction set x86 and all. And then there are these two happy dancing software guys up at the top, right? So that's the definition of architecture, is actually the hardware-software contract, right? And we still, think about architecture and hardware as this ISA, right? Is that there is an instruction set architecture, and now there's this whole momentum around RISC-V as an alternative to x86 and ARM. This is a pretty fine, simple abstraction. But the path to zetta-scale, right, is a bit more, let's say not way more, a bit more complicated than this, okay? I like this picture. Remember this picture, right? A grumpy hardware dude and a couple of, fun software folks. The picture on the left is my favorite picture, right? It's the scale of numbers we deal with, okay? At the bottom, we have really small numbers, angstroms, 10 to the power of minus 10, right? And the top, really large numbers, 10 to the power of 21. That's the scale of computation we are creating. How do we tame these teeny little transistors? How do we put them all together in interesting ways, interesting architectures, packaging and all, to get to the zetta-scale, right? So that is not just, hey, let's get to a RISC-V scalar architecture and you get to zetta-scale. That is one teeny ingredient. So I took liberty to make a different version of the famous, Hennessy-Patterson cartoon, okay? There's still a little more happier hardware dude, think looks a little Indian here. And, still have to deal with the instruction set architecture for scalar. But increasingly, the action is at the system architecture, where you have to deal with power, memory, interconnect, and even more importantly, the accelerators. How are you going to integrate this high-density vector matrix neuromorphic computing? And then on top, you have software architecture. How do you abstract all this complicated system architecture in a simple manner to the software folks? And also some of the AI programming paradigms that Jim talked about yesterday. How do we get software folks trained on dealing with this AI thing? And that's my kind of the angstrom to zetta thing, that across this whole stack, India needs to participate, drive new innovations. And this space, entire from bottom to top, like the conversation with the Israeli Prime Minister, it is very early days. No one is ahead. So it is India's opportunity to grab this. Now, I said zetta-scale, right? So this year, there'll be a 2 exaflop machine in the United States. Okay? So to get to zetta-scale, you need to get to 500x improvement, roughly, right? 500x. So we set at Intel targets, we call them moonshots, right? We said 5x improvement from process technology, the foundational silicon. 6x on top of that, right? So 5 times 6 will be 30 on advanced packaging, memory integration, photonics, power delivery, thermals. So we have teams working on all of this stuff. And this is an area, again, for us to collaborate with teams in India. And 16x in system architecture. And this is how we integrate other forms of computing with the scalar instruction set, whether it's RISC-V or x86. So that's how we broke up. And if somebody smart there is running the math here, it's only 480. We're still short that 20, right? So there's still some opportunities for ideas. And I'll give a quick flyby of what Intel's menu is, right? What we are working on, what our kind of public roadmaps are. The first is our process technology roadmap. This is kind of our most important thing. More than half the company works on it. Today, we are at that Intel 7 is our main production node. Next year, we have Intel 4. And in fact, we have some very high performance data center CPUs with high bandwidth memory being produced on Intel 7. And this chip that I'm holding, this Sapphire Rapids, built on Intel 7, it is the fastest data center chip today. And this is entirely designed. This chip is designed here in Bangalore. Okay? So the lead for the design team works here in Bangalore and all. So that's the state of the CPUs. Now, the second aspect that we work on, like we have in the audience, right, the godfather or the god or the guru of packaging, Professor Rao Tumala, right? So, I feel a little kind of awkward talking about packaging in front of him, but this is Intel's advanced packaging roadmap. For years, Intel had enormous investments and we're leader in packaging. And one of the things about packaging is that if the bump pitch, the pitch you use to connect two chips together, as it gets smaller, you can run more bandwidth, and you can run it much more power efficiently at lower power and all. So when you see smaller numbers, small numbers are good. In general, I think for all transistor-related things, small is good. So today, the Sapphire Rapids that I've shown is at the 55 micron bump pitch. The next one, the Foveros technology, where we stack 3D, we have done a product. This is Ponte Vecchio, which uses 3D stacking with Foveros technology, and that is this one. This is the world's most complex silicon right now. This is the world's most powerful chip. This is what is powering the US SSS computer. And over 100 billion transistors on this, 47 tiles, right? I mean, this is, people think I'm crazy because we haven't done 2 tiles before, right? I went from 2 to 47, okay? And this, 80% of the design of this is done between Bangalore and Hyderabad, okay? So world's fastest supercomputing chip is already designed and done in India, okay? So that's one thing to remember. Now, architectures, right? There is the CPU architectures. CPUs are really good at scalar processing. GPUs are really good at vector processing. Then there is this new thing for AI called TPUs coming. I call them matrix processors. And then there is this, there are probably another dozen of architectures beyond these 3. These 3 are kind of mainstays today. I picked neuromorphic for the async computing and its low power characteristics, and they're really good on sparsity. I think that last one is a bet. It could be anything. Who wins that other 4th architecture? I don't know at this point. But with this advanced packaging, we are able to do what's called hybrid computing architectures. We can combine, instead of before, it's like, hey, there is this CPU, there is this GPU. I can put elements of a CPU, a GPU, a TPU, and a NUPU, the neuromorphic stuff, on the same package in one chip and ship it to my customer, okay? Thanks to, pioneers like Professor Rao, we are able to do this in hardware, okay? So the hardware aspect is kind of largely solved, I'd say, in the sense that we can do it. But there is a software problem. To just support one architecture, the x86 architecture, there are over 20 million developers on this architecture. It took us 30, 40 years to build the ecosystem for one architecture, from low-level software, firmware BIOS, drivers, operating system, developer tools, and all. It took 20+ years to support one architecture. So today's approach that you see is fragmented proprietary solutions for all these new architectures. Every startup comes and they say, I'm doing AI, and tries to build this entire stack that took 20 years. And guess what? All hardware, AI hardware startups, the successful ones, if there are any, they have been acquisitions by Intel. That's all. There's no other AI startup yet that is successful. The reason being software. They all have great, tremendous hardware. So we have been working, and especially as India thinks about RISC-V and all this stuff, this is a problem you need to tackle. If not, it'll be 10 years of work and nothing to show. Okay, there'll be nothing to show if we don't deal with this head-on. So what we have been doing at Intel, we started this effort called One API. Okay, so what One API is, we are taking each level, right, in the firmware level, we call it the level sub-zero. Unify that level for all these architectures. And there is level 0, which is the operating system layer, unify everything in level 0. That is the level 0 API that we have architected. And then there's the level 1 API at the application level, so that you are abstracting the complexity of these hardware architectures away from the programmer, right? That's the key. And we are early in this journey, and I show you the progress, right? On the level 1, we are much further ahead. We got, scalar vector fully covered. It's open source. You can all download and use. And level 0 is, halfway through vector, and level sub-zero needs more progress. Now, the reason I'm putting this is a huge opportunity for Intel and India to collaborate, as India also invests in RISC-V and other architectures at the bottom of the stack. Because if you don't deal with the software problem, like I said earlier, it's a waste of time. Now, there is another software problem. There are two big software problems. Jim kind of hit on it yesterday. Now, programmers, and particularly a vast majority of programmers in India, right, use highly productive tools like Python and very high-level programming tools. What they achieve, so I can give them a zettaflop hardware. The performance they achieve will be at the bottom dot. The hardware entitlement is a zettaflop, but the actual performance they get on the zettaflop machine is this teeny little dot. Guess what? For some of there was a famous paper written by somebody at Google last year. It was called The Room at the Top. I have a question mark. Guess the order of magnitude delta between just a plain vanilla Python program and what's hardware capability is. It's over 63,000x, right? You take a Python program. Now you take that program and this particular gentleman, he moved from Python to Java, he got performance improvement. He moved from Java to C, more improvement. Then he introduced parallel loops, he got more improvement. And then a better parallel loop, more improvement. Then he vectorized it, more improvement. And then he put SIMD AVX512 instructions, and he got 65,000. From where he started, he got 65,000x. Now, how do we make this more automatic? That people, we don't want them to train everybody to think this hardware and figure out all this low-level architecture details. We want, remember the first picture, software guys to have fun, right? Dancing, and the hardware guys to suffer, right? That's the right balance, by the way. it shows my bias. I'm more software and Jim is more hardware. So say, software guys need to take more, so hardware needs to take more pain. So the key elements, just summarizing what I spoke, Intel and India semiconductor mission. If we want to get zetta-scale AI for India by 2027, in fact, like I said, I'd really like to do something by 2025. Right? 27 is, I think, a little late. On the software, one API for RISC-V is a huge collaboration opportunity. And productive AI programming, how do we cover this 63,000x gap? On the systems, there is excellent work going on RISC-V scaler. Professor Kamakoti and all are building the RISC-V CPU and many exciting efforts going on. We need RISC-V vector matrix sorted out for zetta-scale. I've been talking about silicon photonics and some package integration work that we can do in India as well. That's a great, another great opportunity to collaborate. And on silicon, of course, right, manufacturing, process, packaging. I didn't want to go into that because I know that gets covered a lot. That gets more coverage. I didn't want to add to additional thing to that. So if we do all of this, right, this key technologies for zetta-scale, let's come back to the question I started with. Who will be ahead in AI technology by 2030? India. Well, I'd say no. Okay? Well, everything I said is necessary, but not sufficient. Okay? Because I show you these pictures now. Okay? Now, these pictures show the number of servers, right? If India has one server, for every one data center server India has, there are 17 in China, and there are 24 in the United States. There are a quarter of that in Israel. But if you now map it to per million people, okay, for million people, we are off, even relative to the tiny country Israel, right? You can do the math by 40 times and by over 100 factor versus United States. As Dr. Shiva said, right, building technology is not sufficient if you are not using it, right? And the other statement I'd make is that the people who built the best technology already have access to the best technology. For you to build the next best computer, you need access to the best computer of today. You need to be able to simulate your next computer. So India can't be a leader without being a leader in compute. So my ask is we aim for massively increasing the computational capability of India. I have this picture, 50 exascale computers spread all across India. Actually, each computer is a 20 exaflop one, and 50 times 20 would get you zetta-scale. And they're all spread across 100-kilometer radius, because I can get sub 10 millisecond latency between these centers, and you can run entire India as if it was one computer, right? So this is the India that I dream of. This is the India that we should all dream of, and this zetta-scale India already has a name for zetta-scale for thousands of years, by the way. So that we know how to deal with big numbers than any other civilization in the planet. And before I get to question, right? So my team got a little creative and made a little animation for the whole thing of the system, software, and silicon in India, inspired by the movie RRR. And the logo, so hope that plays here. Audio?